General Chemistry 2. Hydrogen peroxide. This is the more practice problems kinetics.pdf. Hydrogen peroxide decomposes rapidly in the presence of iodide ions. The balanced chemical equation for the reaction is this. This data was obtained. What is the average rate of reaction? So, first of all, the interval is 0 to 180, not the whole interval. But even if it were the whole interval, the process would be the same, and it is rate is delta what over delta t, because that's what the rate is, delta something over delta t, and in this case it's concentration of this H2O2. Unpaused. The final minus initial, so the final we have 0.458 and 0.882 is the initial. So let me go ahead and write out final minus initial. T final minus T initial, and then this final minus initial equals 0.458 minus 0.882, 180 minus 0. So I got this scientific notation. What, 2.36, yeah, 3 sig figs times 10 to the whatever, power of negative 1, 2, 3 units, moles per molar, not moles, molar per second. So I have a negative, and I'm taking away that negative because this calculation is really, I should really have a negative 1 over 1 out here, because from rate laws we know that the rate of the overall reaction will be 1 over that coefficient. Coefficient is 1. And then a negative in front because it's a reactant. So carry through that negative and you end up with a positive number down here. Cool. Now, as far as matching that to what we are given as far as units, moles is capital M is moles per liter because it's molarity. And that's exactly what we have. Those are the units that are given. Moles per second equals mole per liter seconds, which equals moles liters to the negative 1 seconds to the negative 1. So that's an answer. E. For the number 2, for the reaction in problem 1, what is the average rate of reaction over the? So you just do the same process. Final minus initial. So for number 2, I'll just take what we had already and change some numbers. If I can get it to scroll, I'll just do this. So this becomes this. Negative 6.44 times 10 to the power of negative 4. And the units will be same as before. Mole liter to the negative 1, S to the negative 1. So yeah, I'm not going to write this. So now, number 3. So for number 3, it decomposes at a faster rate when the concentration is higher, because from here to here is a bigger change than from here to here. And so A. Number 4. So we want to know the order of the reaction with respect to substance A. So we're going to look for 2 experiments where B doesn't change, so that we can actually compare how A changes on its own. So from here to here, A, B does not change, and A does change. Great. Does the rate change? Yes, so it's not 0 order. Let's do some actual math. You want the one to change that you're looking at. So if you want to see how A affects if we compare it to a recipe, if you add more egg, then you'll know how the reaction changes when you add egg.
Right.
You don't want to change any other ingredients because you don't want to know how adding more sugar affects it. You want to know how adding more egg affects it. So if you pick 1 and 3, that's great for looking at how B affects it and finding out the order.
Don't take is 1 and 2.
Yes.
I'm at 1 and 3.
1 and 2. If you're looking at order
For
with
A?
respect to A, you need 1 and 2. Because when we do this equation,
Oh, because it's constant in
1
and 3. I'm sorry.
right? Because when we do the equation, it's going to be concentration 1, and you would just get 0 or 0 over 0. Wouldn't be useful. 2 equals.
Well, you want to put the highest one at the top.
The 1 and 2 don't actually mean anything. You'll want to put the biggest number on top because it makes the math easier. So it's concentrations, and on the other side you have rates. Rate 1, rate 2, and then one of these has to the power of x around it. I believe it's the concentrations. And x will, let me go ahead and invent a rate law. Space down. So I'll invent a rate law for this. How about rate equals k a to the x b to the y, and that's it, a and b. So that way this x actually has a meaning. So we have experiment 1 and 2. I'm going to, when I'm plugging into this equation, I'm going to put experiment 2 on top because it's a bigger number. 3, 4, 8. And experiment 1 on the bottom.
Okay, so the A on this side is the concentration, and the initial rate is the rate. Right.
In the table, yes. You're talking about the second column is concentration, and the 4th column is rates. Yes. So over on the right side, got to be consistent. Six point. Let's see if I can scoot that over. 6.18 times 10 to the power negative 6. 2.006. And then you end up with, looks like 3 to me. 3 to the x. If I were to guess without actually doing math. So x equals 1. Yay!
X equals.
First order with respect to A.
So then if it says write the rate law for that,
then this rate law that I invented or haven't really filled in.
the rate law would be rate equals K times A times B.
Yes, so I put a 1. I really should just.
Times A. We can't put B.
We don't know B yet.
We
It's
don't
B
have
to the
B.
Y. We don't know what the Y is yet. So that's fine. Referring back to this stuff.
They
What-
want B now?
same process. Do
So we're going to use experiment 3 and 4 because 1 and 2 is constant.
you mean 1 and 3?
1 and 3, yeah. Sorry.
Yep. So experiment 1, experiment 3. There it goes. And for B, looks like 3 is the bigger one. So we'll do. And this is now to the y. So this is the rate we're talking about B. Wait a moment. I should really be. Did you say 1 and 3?
1 and 3.
Yes, exactly. 1, 2, 6, 0, 6. 2.
They're also in 1.
Yay! So we have 1 and 1, and so we know our rate law except for k. So that's all that's left to do is find k. Rate equals k. A. B.
So the next question says what is the overall? You just add the 2 up and it gives you 2.
Yep, overall order is 2. 1
Okay.
plus 1.
Referring back to the reaction emission rate of problem 4, what is the numerical value of the rate constant? So now we need to find the rate constant.
Yep, and you just pick any one. Any of the reactions.
So we're going to do the, let's do the first one.
Let's do it. So 0. I'm going to do the algebra first. Rate over A B equals K. And again, this is true if you pick any reaction. So we have this, and the units, it's a overall second order, so the units would be. So we have our numerical value, number 7, okay, D. So now for the units, overall second order, oops. Overall second order. So we know that the units on K are this overall order minus, no, 1 minus overall order times s to the negative 1. So all of these have an s, oh my goodness. All of these have an s to the negative 1. That's not our determining thing. We have to figure out what this m is. I'm getting m to the 1 minus 2, so negative 1. And that's what you said, right?
Yeah.
But now, breaking that out, so we know molar, capital M, is moles per liter. So let me write that as a prettier fraction. Moles per liter. That means that m to the negative 1, which is the same as 1 over m, is going to be liters per mole. Now that's important because that's actually what, liters times times moles to the negative 1, which is not terribly intuitive, but that's what you're going to have. Oh, let me tack on the seconds. The answer is right there, B,
Why did you?
because of this algebra.
Okay.
Number 10.
Oh.
So for number 10, we have our rate law. It looks like this, but we know K now, which would be that. All we have to do is plug in the given numbers. A is this, B is this, and that's number 10.